Hello, everyone, and welcome back to the Deep Dive.
Yeah.
I am really looking forward to today's session because we are taking a look at a topic that I think every single science student in India has encountered.
It's good to be here. And you're right, today is not about memorizing abstract formulas. It's about understanding how nature actually, moves energy around.
Exactly. So to kick things off, let me ask you and everyone listening a simple question. Have you ever seen that classic school experiment where someone takes a lemon or maybe a potato and they stick a copper wire and a zinc wire into it?
Ah, the lemon battery.
Yes. And then, miraculously, they attach a small LED bulb to those wires, and it actually lights up.
A steeple of Class 12 practicals and science fairs everywhere, yes.
It really is. But when you stop and think about it, it's quite bizarre. I mean, it's a vegetable. How can a potato or a lemon produce electricity? Is there a generator hidden inside the fruit?
I can assure you, no, there is no generator inside the lemon. It's not magic. It's pure chemistry. And that brings us perfectly to our topic for today. We're diving deep into Unit 2, electrochemistry, and specifically, we're unpacking electrochemical cells.
Electrochemical cells. Now, for our listeners who are preparing for their board exams, this is a heavyweight topic. But even for everyone else, why should we care about this?
Well, aside from the fact that this chapter carries significant marks in the board exams, which is obviously important, understanding this topic basically explains how the modern world operates. The mission of this deep dive is to understand the relationship between electrical energy and chemical reactions.
So it's about connecting chemistry to electricity.
Precisely. If you understand electrochemical cells, you understand how the battery in your mobile phone works. You understand why iron rusts
Oh, right.
when it's left outside in the rain. You understand how we use electricity to drive chemical changes in manufacturing.
So basically, if you use a battery, a laptop, or drive a car, you're relying on these principles we're going to discuss today.
100%.
That puts it in perspective. It's not just about the marks, it is about the device I'm holding in my hand right now. So let's start at ground zero. If you had to explain what an electrochemical cell is to someone who hasn't opened their NSERT textbook yet, how would you define it?
At the simplest, most fundamental level, an electrochemical cell is a system where a spontaneous redox reaction.
Okay, let's pause and unpack that phrase, spontaneous redox reaction. In simple terms, that means a chemical reaction that wants to happen on its own.
Exactly. It's a reaction that is naturally waiting to happen. It wants to release energy. What we are doing with an electrochemical cell is basically building a trap to catch that energy.
So instead of the energy just being lost as heat, we are forcing it to become electricity.
Correct. We are converting chemical energy into electrical energy.
Okay, I want to visualize this. Because usually in chemistry, we just see equations on a blackboard. But if I close my eyes and imagine this setup, what should I see?
Imagine two separate beakers sitting on a table. In each beaker, you have a metal rod dipping into a liquid solution. These are your electrodes.
Two beakers, two metal rods. Got it.
Now imagine connecting those two metal rods with a wire. And here's the key concept. One of those metals wants to lose electrons much more than the other one wants to keep them.
So, chemically speaking, one is generous and one is greedy.
You could say that. One metal pushes electrons away and the other is ready to accept them. When you connect them with that wire, you provide a bridge.
And the electrons flow.
The electrons flow from the generous metal through the wire to the greedy metal.
And that flow, that movement of electrons through the wire, that is essentially what electricity is.
That is current. That is what lights up the bulb.
It sounds very simple when you put it like that. But I know for a fact that in the exam, they ask about the particle behavior. What is really happening to the atoms?
This is where we need to be precise. There are two processes happening at the same time. First, at one electrode, we have oxidation.
I remember the mnemonic from school. Oil rig. Oxidation is loss.
Exactly. Oxidation is the loss of electrons. This happens at the anode. So imagine the metal atoms on that rod are literally stripping off their own electrons and jumping into the solution as ions. They're dissolving.
So the metal rod at the anode is actually getting eaten away.
Yes, it physically corrodes. That is the price we pay for the electricity. Now, on the other side, at the other electrode, we have reduction.
Reduction is gain.
Right. The electrons travel through the wire and arrive at the second rod. The positive ions floating in the solution around that rod see those electrons, grab them, and turn back into solid metal.
So they stick to the rod.
They stick to the rod. So one side dissolves and the other side gets plated with fresh metal.
That is the physical reality.
Now, I have to mention a massive misunderstanding trigger here. This is something students get wrong in their Viva questions all the time.
What's that?
We established that electrons move through the wire, but students often think that the electrons also swim through the liquid solution to complete the circuit.
Do they?
Never. Electrons flow through the external wire, while ions flow through the internal solution.
Ah.
Electrons cannot swim through water. If you write that on your board exam paper, you will lose marks immediately.
That is a crucial distinction. Electrons outside in the metal wire, ions inside in the liquid solution.
Perfect. And that's the insert safe definition you need to keep in mind. An electrochemical cell is a device where a redox reaction occurs and electrical energy is produced. We specifically call this a galvanic or voltaic cell.
Nice. I like having a solid definition in the pocket.
Yeah.
But to really lock this concept in, I need an analogy. You know I love a good mental movie. How can we picture this flow?
I have the perfect one for you. Think of an electrochemical cell like a water wheel powered by a waterfall.
Okay, I'm picturing it.
The water represents the electrons.
Ooh,
The top of the waterfall, the high point, is the anode. The electrons there have high potential energy. They're unstable. They want to fall.
And gravity is pulling them down.
Correct. In chemistry, that gravity is the potential difference between the two metals. So the electrons flows down from the high point to the low point, which is the cathode.
And on the way down, they hit the water wheel.
Exactly. They turn the wheel. That turning wheel is doing useful work in the external circuit, like lighting up your LED bulb or running your fan.
That makes total sense. High energy to low energy creates work. But in a waterfall, the water eventually pools at the bottom. In a circuit, it has to go back, right?
That's the brilliant part of this analogy.
You can't just have a pile of electrons at the bottom.
No, you can't. In a theme park water ride, there's always an underground pump or channel that takes the water from the bottom pool and brings it back to the top to keep the cycle going.
And in our cell, what is that underground channel?
That is the electrolyte solution and the salt bridge. It allows the ions to move back and forth to balance the system.
So if you block that channel...
If you block that underground channel, the water backs up and the waterfall stops.
So the wire is the waterfall where the work happens, and the solution is the return path to keep the balance.
Exactly.
I've heard another analogy that might work for our listeners who deal with city traffic. Can we think of it like a traffic system between two cities?
That is also a very popular way to look at it. Let's try it.
Okay, so imagine City A is the anode. It's overcrowded with cars. It has high pressure. City B is the cathode. It's empty. It needs cars.
Right. So naturally, the traffic wants to move from the crowded city to the empty one.
So the cars, which were the electrons, jump on the superhighway to drive from City A to City B. That highway is the external wire.
And that flow of traffic is the current. But again, how do we prevent City B from just becoming a massive parking lot?
You need a return loop. You need a service road for trucks or buses to shuttle people back or balance the population. That service road is the electrolyte.
And this highlights a key difference in speed, too. Cars on a highway zoom by electrons, move very fast in the wire. But trucks on a, let's say, muddy service road move slowly.
Right.
Ions in the solution are heavy and slow, but both are necessary. If you close the service road, the whole system jams.
The circuit breaks.
Exactly.
This actually brings up a why question. Why did scientists invent this setup? Why go through the trouble of separating the cities or separating the beakers? Why not just mix the metals together?
That is the fundamental problem this concept solves. How can we convert chemical energy stored in bonds into electrical energy? Before this, the only way we used chemical energy was by burning things.
Right, fire, which gives heat, but you can't charge a phone with fire.
Exactly. Alessandro Volta, way back in 1800, was the first to realize that if you separate the oxidation and reduction, you can force the electrons to travel. Michael Faraday later showed the mathematical connection. They basically unified chemistry and physics.
So if we just mixed the zinc and copper in one bucket, what would happen?
The electrons would still move from zinc to copper, but they would jump directly. You'd get a lot of heat. The solution might bubble, but you would get zero useful electricity. It would be a short circuit.
I see. So by separating them into two beakers, we're forcing the electrons to take the long way around through the wire.
We're forcing them to pay a toll, and the toll is the work they do for us, like lighting the bulb.
That is actually really clever engineering. We're hijacking nature's tendency for our own benefit.
That is what chemistry is all about.
Okay, let's go back to the mental movie, but this time let's do it in high definition.
Okay.
I want to guide the listener through the specific zinc-copper cell, which I believe is called the Daniell cell in the textbook.
Yes, the Daniell cell is the standard example.
Okay, so picture this. We have a zinc rod in a beaker on the left and a copper rod in a beaker on the right.
Picture this. Focus on the zinc rod first. This is our anode. The zinc atoms are literally stripping off 2 electrons each. They oxidize. The zinc atom becomes a Zn ion and falls off the rod into the water.
So the zinc rod is slowly dissolving.
Yes. Now the electrons rush up the rod and zoom through the wire to the other side. That is the motion electrons rushing through the external path.
They cross the wire and reach the copper rod.
Now look at the solution in the copper beaker. It's blue because of the copper ions, CuHo, floating in it. These ions are hungry for electrons. They see the electrons arriving on the rod, they swim up, grab them, and turn into solid copper metal.
And they stick to the rod.
Right. So over time, the zinc rod gets thinner and thinner, the copper rod gets thicker and thicker.
And what about the blue color of the solution?
As the copper ions leave the solution to become metal, the blue color fades. It gets paler.
That is a great detail for the practical exam. Visual observations. Zinc dissolves, copper grows, blue color fades.
Precisely. Zinc is the source, the anode. Copper is the destination, the cathode.
So, bringing it back to our intro, the lemon battery. Is it the exact same mechanism?
Identical. When you stick a zinc nail and a copper coin into a lemon, the citric acid acts as the electrolyte. The zinc nail corrodes, it oxidizes, and sends electrons to the copper coin.
And if we hooked up a voltmeter to that lemon, what would we see?
You would usually see about 0.7 to 0.9 volts.
Why that specific number?
Because that is the difference in push between zinc and copper. Zinc really wants to lose electrons. Copper kind of wants to gain them. The difference in that potential is the voltage. If you used magnesium instead of zinc, you'd get a higher voltage because magnesium is even more generous.
So the choice of metal determines the voltage. Does this apply to the AA batteries in my TV remote?
Very similar. In a standard zinc, carbon, or alkaline battery, the outer container, the metal can itself, is made of zinc. That can is the anode.
The container is the fuel.
Yes. Inside, there's a carbon rod acting as the cathode, and instead of a liquid, they use a moist paste as the electrolyte. That is why we call them dry cells.
So when my battery dies, what has actually happened inside?
It means the zinc container has corroded so much that there are no more zinc atoms left to give up electrons. The chemical fuel is finished.
So a dead battery is basically just an empty shell.
In a chemical sense, yes. The reaction has run its course.
There is one more component we touched on briefly, but I know it's a favorite topic for examiners. The salt bridge. We called it the service road. But why is it so critical?
This is important. Without a salt bridge, the cell stops working in seconds. Here is why. As zinc dissolves, the beaker fills up with positive zinc ions, Zn. The liquid becomes too positive.
Okay, it gets crowded with positive charge.
And that positive charge starts pushing back against any new positive ions trying to enter. It chokes the reaction.
Right.
On the other side, the copper beaker is losing positive ions, so it becomes negative.
And that negative charge would repel the electrons trying to come down the wire.
Exactly. So the flow stops because of charge accumulation. The salt bridge is usually a U-tube filled with a jelly that releases ions. It sends negative ions to the zinc side to neutralize the excess positive charge, and vice versa.
So it maintains the balance.
The key phrase for your exam is, it maintains electrical neutrality. If you write that, you are safe.
Maintains electrical neutrality.
Got it.
Okay, we've covered the visualization, the analogy, and the real-world examples. Now, I want to make sure our listeners are bulletproof for the exam. You usually have some clarity lines or golden rules.
I do. These are the B4 clarity lines. If you keep these 6 points in your head, you can solve almost any conceptual question in this unit.
Let's go through them one by one. Number 1.
Electron path. Electrons flow from anode to cathode through the external wire, never through the solution.
Right. Wire only. Number 2.
Ion path. Positive ions flow toward the cathode compartment through the internal solution.
Number 3.
The locations. Oxidation is always at the anode. Reduction is always at the cathode.
I use an ox and red cat to remember that. Anode oxidation, reduction cathode.
That is a classic mnemonic. Number 4 is where students get confused. Galvanic signs. In a galvanic cell like a battery, the anode is negative and the cathode is positive.
Wait, let me clarify this. In physics or in electrolytic cells, isn't the anode positive?
Yes, and that is the confusion, but listen carefully. In a battery,
Huh.
a galvanic cell, the anode is the source of electrons. Electrons are negative, so the source must be negative.
Okay. Source equals negative equals anode. I will lock that in. Number 5.
The bridge. The salt bridge is essential to maintain electrical neutrality. Without it, the circuit breaks.
And finally, number 6.
Open circuit. Without the wire connected, a potential difference still exists. The voltage is there, but no current flows.
It's like the water sitting at the top of the waterfall with the dam closed. The pressure's there, but nothing is moving.
Exactly.
Those are excellent. I feel like if a student just writes those down on a flashcard, half the chapter's done.
Absolutely. Those are the pillars of the topic.
Okay, let's wrap this up with a short summary. We've covered a lot of ground today. If someone's zoned out for a minute, what is the core recap they need to take away?
Let's sum it up in 4 points. Core idea. Electrochemical cells involve electron transfer between chemical species redox reactions. The image. Think of the waterfall electrons flowing downhill from high energy at the anode to low energy at the cathode. The example. The zinc-copper reaction in a battery is the perfect example of chemical energy turning into electrical energy. And final exam tip. Electrons move outside in the wire, ions move inside in the solution.
Perfect. Now, before we sign off, I have one final thought. We talked about batteries dying. We talked about the zinc getting eaten away. Is that the end of the story? Is it a one-way street?
Well, for the cells we discussed today, primary cells, yes. But think about your phone battery. You use it, it runs down. But then what do?
I plug it into the wall socket.
Exactly. When you plug it in, you're pumping electricity into the cell. You are forcing the electrons to go backward. You're pushing the water back up the waterfall.
So we're reversing the chemistry.
We are literally undoing the reaction, turning the products back into reactants. That is the principle behind electrolytic cells, and it's the flip side of this unit.
That sounds like a fascinating topic for another deep dive.
It definitely is. It's how we recharge batteries and how we purify metals.
Amazing. All right, everyone. Next time you slot a battery into your remote or see a piece of rusting metal, visualize that invisible waterfall of electrons. It's not magic. It's just chemistry doing its job.
Keep learning.
See you the next deep dive. Goodbye.